Hi, welcome to the Spotlight Report. I'm your host, Logan Graves. This is a monthly podcast where we dive into topics that pique our interest. They typically cover optics and science, but honestly, they can be quite broad. You can find out more about the Spotlight Report and find all of our episodes, as well as comment or like the podcast, on our new location, which is on the ELE Optics Community Forum. That location is community.eleoptics.com, and you'll find the Spotlight Report there. Thanks for listening.
So it started with, hi, this is a Spotlight Report? Sure, let's
Okay, this week I am sitting down to speak with Eric Goodwin, who wrote the field guide to Interferometric Testing.
Optical testing.
Optical testing. Darn. Well, I promised I would get it wrong.
Yeah.
I've only read this a little bit, but the times that I have read it, it was in a panic because I needed to figure out what was wrong with my test, and it's been extremely helpful. Eric currently works at Nikon Research Corporation in Tucson, Arizona. So without further ado, how did you get into optics, and how did you end up in Tucson, where it's exceptionally hot right now?
Yeah, it's a rough day today. So I grew up in Oregon and wanted to go somewhere new for college and ended up at the U of A for a variety of reasons, but it did not include optics. Met a guy, lived in the same dorm, who had come from the East Coast to specifically do optics at the U of A, and I thought, well, that sounds pretty neat. And eventually worked my way over to Op Sci, and Dee Dee Lawson was working at the front desk. And
Right.
I asked if there was a professor that I could talk to, and she recommended Jim Palmer. And he used to have his presentation called What is Optics? And he brought me into his lab, which was stacked to the ceiling with all kinds of old gear, and gave me that presentation. And I was pretty much hooked at that point, and changed my major within a month.
This was your freshman year?
Freshman year at the U of A.
And were you already in engineering?
I was in engineering,
Okay,
but I
okay.
didn't know which
The specific,
kind,
yeah.
to do. Yeah.
I was kind of similar in that I had started in biomed engineering,
Yeah.
and through a massive stroke of luck, someone I knew Jim Wyant, and they told him, not someone I knew, my mom, they told him, he's going to do biomed, and apparently Jim said, no, he's not. He should do optics. So that's how I got into it. So I'm assuming it's safe to say you liked it. You went through undergrad, and then did graduate school. But I guess what part hooked you? When was it that you said, "Oh man, this is it"?
It just seemed like it was so applicable to so many different aspects of just general life, but also science. As a kid, I was always into astronomy, but once I investigated that as something to do, I realized I'd be spending time on mountaintops and working in the middle of the night.
Yeah.
Although maybe that's not so true anymore. Just seemed like a great mixture of a lot of the things that I was interested in, and the possibilities for a career in optics seemed so vast and varied that I could see myself being really excited about a lot of those different options.
Mm-hmm. And so when you went into graduate school, did you continue in Tucson, or did you go somewhere else?
I did. So I actually went to the U of A for 9 years straight.
Okay.
Pretty much.
Okay. I did a similar thing. It took me 10 years.
Okay.
I did end up doing biomed with it, but yeah, it's kind of crazy at the end to leave and realize I've done this 10 years. It seems like a long time at the time.
Yeah.
When did you, or did you, I guess, what was your graduate work on? Was it on interferometry or metrology methods in general?
So I actually, as an undergrad, was fortunate to be part of the NASA Space Grant Program.
Nice.
And I was in Harry Barrett's research group. And I think I was the first intern that they hired, but the only reason they hired me is because they didn't have to pay me, because it was paid by the grant. So it was, in their mind, more or less risk-free. Ended up working out, and so I worked there for almost 3 years on nuclear medicine-related research. And it was interesting, but I knew I wanted to do something else. So in graduate school, I was in John Greivenkamp's group. And my initial project was interferometrically related.
Okay.
I could talk a little more about that if you want.
Yeah, I guess at a high level, what were you investigating?
So we were hired by a leading optical what's the word, medical company, I guess. They make contact lenses. And so my project was to figure out how to measure the refractive index of soft contact lens material, which of course is a significant percentage of it is fluid. And so you have to measure it while it's submerged. And yeah, so that was the beginning of the project.
Right. Huh. So was that project your entire thesis? Like, did that go for the full?
I was quite fortunate that there was a handful of other things that we worked on within the group, and I had parts in. But once I was assigned that project, I got to take it from the start to the finish, and
nice.
So yeah, it was great.
Nice. I'm really curious, and you can obviously opt to not talk about this if you want, but I'm really curious what it was like working under Dr. Barrett versus Dr. Greivenkamp. They're both very big personalities, very big names in optics. Yeah, I don't know if you're open to talking about it.
Sure, yeah. Well, so working for Dr. Barrett, he had a huge group with multiple professors working for him. And officially, I reported to one of those other professors who was in the nuclear medicine field.
Okay.
But when I first started, I think this was during my sophomore year, so I had just started geometrical optics. And at the time, Harry was writing his big book, which I can't remember, Foundations of Image Science.
Yeah.
It's massive. And
we just call it Harry's book, right? Like, it's a big book of optics, or So
I had a little desk I think it was in the copy room, and the only other person in there was a woman who was taking Harry's notes and writing it into the LaTeX format to make the book. But she wasn't an optics person or a physics person at all, so she was just following the notes.
Yeah.
So that was all going on. But anyway, so Harry wanted me to meet with him once a week for an hour.
Yeah.
And
low stress.
I was so intimidated. I had no idea what to talk about. I knew I didn't know enough to even scratch page 2 of his book.
Yeah.
So those meetings didn't last very long. He was, but it was, there was a lot of group meetings with, again, conversations that I just wasn't equipped to follow at that time. Yeah. John, on the other hand, was pretty hands-off. He was really excited he was very involved with the new building, which now is not the new building anymore, but at that time, the one with the columns and all the windows facing north, that was his project. He was the main person from the department. So actually it was kind of funny. We used to tease him because we would try to start group meetings, and we'd do them a couple times, and then he would declare that he didn't want to do them anymore. So, but he was always available when we needed him. And I think it actually served all of us really well because it taught us how to be more independent and learn from our own mistakes more quickly than if someone had been there all along making sure we didn't make mistakes. So
I had John for various courses throughout those 10 years, but he was also on the committee for the oral exam for geometrical optics.
Right.
And he had asked me a question, which was, why do binoculars have the focusing dial? And for me, at the time, I was like, I'm just stressed. I'm trying to get through this. And Chris Summit, someone that his advice was always, if they ask you a question, take a sip of water and pause for a moment. Right, yeah, there you go. Pause for a moment, figure out what they're asking you, and then answer that. So John just kept asking, why do they have a focusing ring? Blah, blah, blah. Why do they have a focusing ring? And it went on for 10 minutes, and finally, the answer was, well, things aren't always at infinity. They might be at different locations. That was all that he wanted. And we finished the exam, and I passed, and John came up and he's like, why did it take you so long to say that? It wasn't a hard question. And I told him I was just stressed. And he then followed up with, why did you have to do the oral exam? Why didn't you pass the written part on the comps? And I told him I was stressed. And he said, yeah, you knew all this stuff. You're just wasting time here, doing, being worried about these answers. And it was, at the end, it was like, that's really cool. I passed, so I was able to think that. But
right.
But it was like, oh, okay, kind of like you were saying. He knew the level that you were at.
Yeah.
And, I don't know, he trusted you. you'll figure it out. So
yeah, I think it's about learning to trust your own abilities, or trusting to know when you know what you're doing and when you don't.
Yeah.
And yeah, it was ultimately, I think, worked really well.
Right.
There were people that joined the group and didn't like that style and would have to leave, but it wasn't anything personal. It just was the way that they wanted to learn. So
I think your advisor and how unique that relationship is underrated in some dimension by a lot of students.
That's a good point.
So you went on, and at some point you wrote the field guide. When was that?
So that was during graduate school, towards the end. So John, of course, Greivenkamp wrote the first one on the geometrical optics, and then he was recruiting various people to write the next group of drawings. I think mine was the 10th one.
Okay.
So of course it was mine with Jim Wyatt.
Okay.
And it was... John originally wanted Jim to write it because, obviously,
right.
I don't need to explain why. But Jim was, at the time, head of the department, and I don't remember if he was president of SPIE at that time, or he was very active in the society. So he, I think, told John, "Nah, I don't have time to do that." So then, at some point, John suggested, "Well, what if I gave you a student to do it, and you just review the work?" And so that was eventually what came about from that. So I would take Jim's notes and try to put it into the format and try to describe things. And I had taken his class and Professor Milster's class. And so, and it was towards the end of my work, and most of what I had done was on interferometry. So, but of course I did learn a lot. I learned the material in a lot better detail than I would have from just taking the class. So it was great because I had an opportunity to meet with Jim weekly to go over my progress, take his feedback, and we're both huge basketball fans, U of A basketball fans. So that was one thing we always would check in on, especially during the season.
Right. So. It would be happiness, and then
inevitably disappointment. Yeah.
So after you graduated, did you immediately start the position that you're in, or?
I did, yeah. I had my second child was born a week after my PhD defense. My daughter was born less than a week before my comp exams, prelims. So I actually took the prelims with the hospital bracelet still on from she was home from the hospital, but anyway, I didn't time those things well. But yes, I went straight from graduate school, took a couple weeks off, and then came to this current position. So I've been here. So it's easy to know how long I've been here because it's how old my son is. So I've been here 17 years.
Oh, okay. Perfect. Makes it straightforward.
Yeah.
So I probably know just as much about not only where you work, but also much less what you do as anyone listening. So can you kind of describe that? I mean, everybody's heard of Nikon.
I hope so.
And when Chris had told me that he was going to work at Nikon, I was like, they're not here. You're moving? And he said, no, I'm not moving. I mean, I'm going to be in Tucson. So,
So it actually started when I was in graduate school. So David Williamson was my first boss at Nikon, and he is famous within the lens design field he's retired now, but he designed the lithography lenses, and is one of the few people in the world who was designing the highest NA, highest performance projection lenses. And he was living in England. Nikon hired him and said, we'd love you to come work at our office in the Bay Area in California. And he said, no, thanks. I don't want to live in the Bay Area. It's too expensive. I already have an expensive house in England. So he suggested Tucson. And he thought, well, I could start pulling students out of the U of A. And so when I was a student in John's group, he had a small project that hired me and another student to work on. So I got to know each other then. And then that other student got hired at Nikon, and then I was hired a couple years later. So we had just the three people there. And so this is the company that I actually work for. The name is, like you said, Nikon Research Corporation of America, and we're headquartered in the Bay Area. And as the name suggests, we are an American company that does research for Nikon.
Yeah.
And the optics group is pretty much entirely here in the Tucson office, and then in the California office is mechanical engineers, controls engineers, electrical engineers, software engineers. So we've done a lot of work traditionally for Nikon's lithography tools.
Okay.
And but that was probably the first 10 years or so. That was almost entirely what we worked on.
Mm-hmm.
More recently, we've changed gears to a much broader set of optical problems. We are working on metal 3D printers. Nikon is currently selling a couple different models, and in addition to the optics for delivering the energy to melt the metal, we're trying to implement a lot of optical feedback to the process as you're printing, because of course these builds can take a really long time,
right?
And you'd like to know how they're doing.
Yeah, you don't want to wait till the end and say, we have to restart it.
Exactly. Yeah, and then melt it all down, or however they recycle it. So that's one of the areas now that we're working in.
So, I guess part of the answer is going to be you learn it over time, but that seems wildly different to me than measuring the refractive index of a contact lens, right?
Yeah.
Even going into it of primarily work on lithography lenses at the initial level. So how was that? Like, how did you learn it, and is that fun, or was it just stressful, or?
So it's it's interesting. We talked about prelims, and when I took them, I think there were 10 courses that were covered, everything from quantum to geometrical optics. Yeah. And I remember when I passed, I was like, oh, I'm not going to have to worry about quantum optics ever again, or any of these other things. But then within 6 months of starting this job, I had to go back to notes for, I think, all but one of my prelim classes for various tasks for different projects. And to be clear, I had never worked on lithography lens design. That was David's job. But I did get to work on other aspects of the lithography tool. And I think that's one of the best things about this job, is that pretty much every day is an opportunity to learn something new. Mm-hmm. And that's continued the whole time, which makes it really engaging and rewarding. Although I was a little bit overwhelmed on my first day, and this is a pretty embarrassing story, but I think I'll tell it anyway. So the lithography industry has all these terms related to line edge roughness and dose control, and how resist works, all these things that I wasn't really familiar with. But, they really aren't that complicated. You just have to learn the terminology. So David was explaining the line edge roughness and how, they have the 2 sigma limits on how well the line edge roughness has to be. And I was focused really hard to try to remember all these new acronyms and learn everything. And so I had to interrupt him, and I asked him, well, what's the relationship between 2 sigma and sigma? And he looked at me like, it's a factor of 2. I was so focused on the acronyms and everything. I completely, Anyway, so.
You got to get that out of the way early on, right?
Yeah.
Any job.
Not going to say that was the last mistake I ever made, but.
So I guess I'll kind of shift a little bit, but it feels to me. I think a lot of optics education, my experience was, particularly through grad school, of like, okay, well, I think lens design's interesting, so I'm going to take these courses and specialize. And I've met a lot of people who've done just that, right? They specialize and they become exceptional at that domain, and not so much outside of it. And maybe we'll touch on this with metrology, but I'm curious what your thoughts are on, kind of learning a broad array of topics versus specialization.
In terms of my experience, or what?
I guess in terms of
look for.
I kind of want to say for people going into optics, I also think, and you probably know this better and from a different domain than I do, but optics is getting broader. Like you said, it's everywhere. Like everyone says, it's everywhere. But I think that requires a more, if not diverse skill set, at least an ability to jump on something new pretty quickly. But I'm curious to hear your thoughts.
Yeah, it's a good question. I think my opinion about, for me, the transition from undergraduate to graduate school was Not so much that it was new material, mostly because I had been to the U of A for undergrad as well, and a lot of the same professors. But it was having the opportunity to step back and see the connections between all the different parts of optics. Of course, they have to break it down and say, okay, now this class is E&M, and this class is solid state optoelectronics.
Right.
But at the end of the day, it's all physics, and it's all related. And so once you're able to start, or for me, when I was able to start seeing those connections as a graduate student, that helped a lot. See, I'm not sure I'm answering your question exactly.
No, I mean, I think that alone is a good answer, right? That when you do kind of step back and kind of look at it from a 1,000-mile perspective, it is all connected, and I think that can be easy to forget.
Yeah, I guess that's part of it, and then I think it's also you really learn how to learn as a graduate student, and undergrad as well. But if you are successful in a graduate student or in a graduate work, you become the expert on what you're doing, more so than anyone else. Even your advisor, you should know more about what you've done than your advisor does because you did the work.
Right.
And you kind of just, with more experience and more practice, I think, in your career of that, you just get more experience, a broader horizon of things that you've done. And then you just kind of keep those as like your tool belt. And you have these things to fall back on when you face a new problem. You go back to those tools. And my specialty was interferometry, metrology more generally. And I do still apply that to most of the projects that I work on. Not all of them. But as my coworkers would tell you, my favorite solution to a problem is to use fringes somehow. It's even the name of my Wi-Fi network. So now I can tell you the password, but that's, so you'll end up probably developing your own favorite tool. If there's so many other different kinds of measurement approaches that people are working on, but it's what you know best, and you know what it can do and what it can't.
So I'm curious. Sorry that these are kind of coming from all directions, but I talked with David Schaefer one time, who also worked on lithography lenses, and another person who was a really interesting guy and had a lot of experience at like a super high level engineering systems domain. But they both brought up phenomenology, and basically this concept that they try their best to go into new projects as unbiased as they can be, right? So my graduate work was in deflectometry. Trying to always hint at, no, I assure you it's just as good as interferometry, and never quite proving it. But any new project that I go into, especially in graduate school, we should just use deflectometry. It's great. And I think it took me time to learn, there's a right tool for the job, maybe. And it's not bad to have, like you're saying, like your knowledge, your domain knowledge to say, well, I know deflectometry inside and out, and I know when it will really be good and when it really won't be. I'm curious if you have thoughts on that, particularly in your 17 years at Nikon Research.
There's definitely been times where interferometry was not the right approach, and especially earlier on in my career, I think I tried to apply it sometimes when it maybe wasn't the best solution. One thing I've been trying to be conscious about the last several years is very much like what Dave Schaefer was saying, I guess, is you have to be able, it's really hard, but I'm not saying I'm good at it, but I'm trying. And that is to question or understand your assumptions about when you're trying to solve a problem. And a lot of times that's where, and I've read this before, this is not some unique idea, but it seems really applicable to research and development and engineering, is, it's easy to have, we have these preconceived things that we know really well, and like you say, deflectometry or interferometry. If you're able to realize that and then take a step back and try to see, is that biasing the answers that I'm coming up with? And usually the answer is yes. And
right.
So,
So I guess how have you evolved over your career in how you approach new research topics, right? I'm assuming how you might, like you said, how you might approach some problem that pops up. I'm positive the research problems that Nikon throws your way are really, really hard. So how have you shifted over your career versus the start to the end? Not only, I guess, on how you approach them, but even how you start to formulate thinking about them, like at a high level or like a system level.
I think it comes from exposure and experience with lots of different kinds of systems. It's really hard to find time during the week to read the latest SPIE releases, or it's great to go to conferences, but by day 4 you're feeling a little full. But the more exposure that you can give yourself to those things, or that I can give myself to those things, it almost gets to the point where it feels like the subconscious is suggesting things. And you just kind of have to let that relax a little bit and let that happen. It doesn't happen overnight, but I think I feel like it's a little bit related to the whole 10,000 hours thing that was popular about 10 years ago. I think with Gladwell's books about, anybody can do. I don't think that's quite true. I could spend 10,000 hours trying to be a painter, and it would never happen.
Right.
So,
you could paint something; it would just be abstract.
Right. No one would care. So, it's hard. Every time is different, and everybody brings their own perspective. And I think, you always hear the saying, there are no bad ideas. I mean, there are plenty of bad ideas, but they should be said, because they shouldn't be discouraged. They should be encouraged, because those lead to other better ideas. All the time. I see that. Something
I've noticed in people that I've tried to rope into being my mentors over the years has been, like you said, there's a lot of kind of off the cuff, I think it's this, or maybe this. But then there's a really robust de-risking period after that. So at the start of a new project, they might say, I think you could do that, or maybe you could do this. And once we really start to choose something, you start to say, okay, they start to say, let's go down the list and see what the risks are, and what resources that might take. And not only does it, but how well might it meet the project requirements? I don't know. I guess I'm just telling you what people that I've worked with have done. I'm curious if you have thoughts on that.
That sounds like a pretty good practice to do. I think the only minor thing I would add is that once you have an idea that you think could be plausible, is to try to rank the issues. And early on in my career, I would look at that list and I'd say, well, I know how to do 1, 2, and 3. 4, 5, and 6, I don't know how to do. So I'm going to do 1 through 3 first.
Right.
But that's not the right way to do it, I don't think, because if one of those last 3 doesn't work out, then it was a waste of effort to do the first 3. And so it's hard to force yourself to do the hardest thing first. Maybe not the hardest thing, I guess, but the thing that seems the biggest risk for the idea or for the project. Addressing that first.
You've described my early career very accurately in that.
I don't think we're alone in that.
Yeah. Hopefully other people can learn from this. So I don't want to take up too much time. I collected various questions from other people who were excited when they heard I was talking to you. So I might fire off some random ones if you're okay with that.
Sounds good.
One of the first ones was, what is your favorite interferometer layout? and why? They had a preferred answer, but I'm not going to tell you what it is.
Are you going to be able to tell me who asked these questions later?
Yeah, definitely.
Okay, all right. I'm curious now. That is a good question. I don't know. I guess I think shearing interferometers in general were underutilized. I think not a particular arrangement, but there are some shearing interferometers that are, commercially available now. Other ways that have a lot of benefits and simplicity compared to some other things.
I guess what's the benefit? Like when and why would I use that over?
Well, you get a nearly common path through your system if you do, lateral or radial shearing. And so a lot of things depending on the accuracy that you're going for, a lot of environmental drifts, things like that, just get more or less canceled out. Mm-hmm. Okay. At least to first order. At the higher level, they still matter, but yeah.
Okay.
There's the point diffraction interferometers.
Yeah,
pretty cool
that was another question I had, so we can jump into that.
I was trying to remember the name. I was going to do your strategy of drinking water try to, I couldn't remember the name because I can rarely remember the names of things, names of formulas. I don't know. Anyway.
So what can you describe the point diffraction interferometer and more so kind of what makes it special?
Now I'm going to worry I'm going to get this wrong.
That's why I asked you and didn't try to describe
so
myself.
See, that's why I'm not sure I'm naming the right interferometer. So this was, maybe it was the Sommergren, there was a guy named Gary Sommergren interferometer where used a single mode fiber to create the measurement beam. Mm-hmm. So, it's a Gaussian beam, and then arranged the reference in such a way that the reference mirror bounced off the edge of the fiber ferrule, which is nice and flat and polished. And so now you have a nearly common path arrangement with a beam that's well controlled and very little optics to worry about in terms of calibration. Yeah. I know I'm not fully describing it, waving my hands around, but I've never had a chance to build or use one of those, so I don't know actually.
So that surprises me why it didn't take off. Like, that sounds phenomenal, right? There's not a bunch of other stuff to worry about.
Yeah. Concave optics, it'll work for. Yeah. Obviously, convex gets hard for a lot of these techniques, but
nonetheless, that's a huge domain.
I think it was developed early in the days of EUV, extreme ultraviolet lithography, and I think Sommergren, I don't know if I'm pronouncing his name correctly, worked at Lawrence Livermore Labs, and I think that's where he developed it because they were some of the first people to work on those mirrors. Yeah. And the accuracy required was just what you... Yeah.
And I should add as well, we'll put links in the published podcast to these papers and your field deck, etc. So you've mentioned now Common Path twice.
Yeah.
My question from young me when I was a freshman or first year graduate student was, and I remembered it because I asked a professor and they looked at me like, what are you doing here? Was, can you explain retrace error to, like, in a simple way, in a dead simple way?
Okay. So in an ideal case, your test optic will be perfect and all the light will be normally incident on the surface in a Fizeau arrangement, for example, and it'll retrace itself back through the system. And the reference beam is also perfectly normally incident to the reference surface, and so the rays trace the optics in the same way. As soon as your test part deviates from the ideal shape, now the rays go through different parts of the optics on their way back, and depending on your accuracy that you're shooting for, that can quickly become a limiting error for how well you can measure your surface because the light's going through a different part of the glass.
Right. Okay. Where does standard interferometry start to fall short? When might you start to say, I've got never right, of course, right.
All right, yeah.
That's one of those bad questions. Like you might have a project and you have a standard interferometer with a transmission sphere. At what point do you start to say, we're going to need something different?
Well, so spatial resolution can start to become a problem when you have a larger aperture, depending on what the optic is made for. Traditionally, spherical optics, there's no fine tool involved. But once you're getting to A-spheres, now a lot of times it's a diamond tip or some other technique like that. And it can introduce spatial frequencies into your surface that you can't see with a traditional Fizeau interferometer. Stability, the influence of air turbulence was one they always talk about. Just the overall accuracy of your system. For cameras and things like that. Obviously, the visible wavelengths haven't changed, so the wavefront aberrations requirements are not changed. But in the cutting edge fields like LIGO, where they're measuring the gravitational waves, or obviously lithography, those sorts of things always have to be pushed.
Yeah,
and that's where the development happens.
I guess what developments are you seeing, or have you seen, that you think are the most exciting for metrology?
I think I don't remember when, 5-6 years ago, when I first learned about optical combs. Maybe it was a little longer ago than that, but it was a great talk. I think it was at Photonics West about a Japanese research group that was using them to measure the elevation of their instrument. Basically, gravity change. Right. They could use that optical comb to tell how far to within.
Because it's affecting that center wavelength.
Yes.
Or I guess I should rephrase this. Is that what they were concerned with?
They were just showing how accurately these atomic clocks could be used. They were based on the optical combs. And it was, the whole cesium atom standard. I guess we've gone orders of magnitude beyond that for timing. So it was, I think it was something related to, obviously I don't remember all the details, but it was, what's the word? Relativity with the timing and the motion of these things. But one of the other limitations of interferometers, a lot of times, if you're trying to measure anything absolute, right? They're all relative in the standard basic configurations, but optical combs can measure distances in an absolute way, or they're using them in spectroscopy, they're using them in other fields, and I think it was won the Nobel Prize in 2005 or something in physics, and you're starting to see them commercially available now. So I think they're kind of expensive as far as I understand, but it's not a casual, like anything else, it will probably come down, and I think it's pretty interesting.
I know next to nothing about them. I should read more about them, but the reason I had asked is that at my work, we've had customers where, like you're suggesting, getting the utmost accuracy of your test for your final surface figure is really important. And so every little thing matters. And one of the things that I was totally oblivious to was the fact that if I test something, up on top of a mountain versus down at sea level, my center wavelength is going to be a little bit different. And that has impacts on the final uncertainty stack up. So I'm curious how does metrology connect to the thing you care about at the end, right? Like, how do I, and metrology is such a broad field, but to give you an example, it's one thing to say, okay, we've designed an off-axis A-sphere or part, and I'm going to get some null optic or some configuration to test it. But when I test it, if it's off-axis, I'm going to get some really funny distorted thing. And so there's extra steps that need to be taken so that I can interpret it, so that at the end of the day, when I have a real thing and put it on a polishing machine or diamond cutting tool, I can say, no, cut here.
Yeah.
Right? So that's an example from my experience, but I'm curious how you would describe that. Like, where does metrology fit in, and why is it important?
I think the short, obvious answer is step 1 is, can we design something? Step 2 is, can we fabricate it?
Yeah.
And step 3 is where metrology comes in, is, can we verify that we made what we designed?
Mm-hmm.
Otherwise, it won't work.
Right.
And in the case of the systems that you described, the imaging or whatever application, it just won't be as good as it could have been. So I fortunately, I don't have to convince people at work about the importance of metrology, because Nikon makes lithography lenses and all these other very high accuracy optics. Some of the things that they, not me, can do in Japan are really unparalleled. So I'm fortunate that I don't ever have to justify why this is important to coworkers. But but yeah, I mean, I think that really is the fundamental answer. I've seen wavelength variations from going to the mountaintop, like you said, things like that. Ultimately, what you're trying to do at some point will either not work to the level that you want, or it just won't work at all if the metrology is not good enough. One example that I got to work on quite a bit is the wafer stage on the lithography tool. So when I first started, what they were using were heterodyne interferometers to measure mirrors mounted to the sides of the stage. But the wafers are 300 millimeters in diameter, which means the air path could go anywhere from about 5 millimeters to 305 millimeters single pass.
Yeah.
And no matter how hard you try to control the environment in there, the variations in the refractive index of the air, based on humidity, pressure, temperature, if there was a truck driving by, then that doesn't change the index of refraction. But anyway, all those things eventually blew the budget, and you could no longer print working circuits, at least with a high enough yield. And so we had to come up with an entirely new approach. And that approach was to put gratings on top of the wafer stage and use encoders with a very small air gap.
Yeah.
And
try to minimize that uncertainty that you're going to get.
Yep. And then design the encoder to equalize glass path, equalize air path, equalize, make them as much common path as possible. Yeah. And anyway, so you just keep finding the whack-a-mole, finding the thing that's sticking up the most.
So we're about at 4:50. Do you mind pushing it 5 more minutes?
Sure.
Is that
okay?
That's fine. Okay. Yeah. Are relative measurements underrated? So Are
relative measurements underrated?
I've heard a lot of, particularly people who don't do metrology will advocate for what is it? Just what is it? What's the final number? And not appreciate compared to what, right? Like what's that stack up going to be? Or like you said, I mean, for a lot of interferometers, you're going to compare to some null optic. So I'm just curious.
I know I used the word absolute earlier talking about optical combs, but really, if you think about it, every measurement we make is relative. There is no such thing as an absolute measurement. So I'm not sure, underrated, overrated. I think it's just, that's all we have.
It's just what it is.
It's just, and I think you have to appreciate the measurements that you're making, you have to understand, it's kind of like, the assumptions that you're making about trying to solve a problem. You have to understand, well, what am I actually measuring it relative to?
Yeah.
And is it relative to the atmospheric pressure of the room that I'm in? In fact, we have kind of a joke in the lab is that really all we do is build very expensive and complicated thermometers. Because at the end of the day, when you've gotten everything else down, you pretty much always have temperature to deal with at some point. So just, figuring out what is it you're really measuring compared to what.
Should more people come to Tucson?
Of course. Yeah. Although bring water with you, I guess.
Right.
No.
And I guess follow on to that, should more people go into optics?
Yeah, I think it's going to continue to be a growing field. I think there's going to be a huge variety of things that you can work on within your careers. I mean, looking at the list of people that you've talked to, they're kind of all over the place in terms of what kind of optics they work on. And I think there's something for anyone who's got a level of interest in it.
Yeah. So I guess along the same vein, whether it's a company or a research group, just for you, again, this isn't an absolute statement, but who do you think is doing some of the more interesting stuff in optics?
In terms of at a university or just?
Frankly speaking, I'm thinking in terms of Tucson companies and or the university. But I think for someone who, who's considering, okay, well, sure, optics sounds interesting to study, but what does it mean to do it? What are the things that, at least for you, you think, oh man, like this is amazing. Obviously, Nikon Research Corporation is doing amazing stuff, but out above and beyond that, are there any companies or people?
I think that I mentioned earlier that I've always had an interest in astronomy. I think from a career point of view, for me personally, I'm not sure I have the patience to work on a project for 10 years and then wait for it to reach its destination, for get on a ship for 10 years to launch. But I love following what's going on, and one of the projects that I heard about recently was Roger Angel working on how do we find exoplanets. And the traditional approach as well, we just build a bigger telescope, and of course he's been doing that with the Mirror Lab and all of that. But his newest idea has to do with 1,000 or more 1 meter mirrors, and incoherently combining all the light to a spectrometer and just collecting one photon at a time. And, it seems pretty exciting what we could learn from that. I almost studied adaptive optics when I was in grad school. I almost went into that kind of group, and I still follow that. I think that's pretty interesting work. I haven't followed it closely enough to know what's new in it, but I think just the one thing I always tell students who I meet who ask is just go knock on the doors of different professors and find out what they're doing, because 99% of the time they really love what they're doing. And they're going to be really happy to share. Right. So.
Okay, well, the last two questions, they'll be off of optics. So I have a strong opinion about this. Should people do more at a university level? Should people take more gen eds? And at a personal, not university, because there's a real world outside of that, should people do more things not just studying optics? So, like for myself, I go to work, I work on interesting stuff, and it's taken me some time, but it's very tempting to want to go home and say, like, oh, I want to read up on new math that applies, or optics that applies, as opposed to going and doing something unrelated, like playing basketball or whatever.
Yeah, I have a feeling I'm going to say something that you agree with, but I think it's really important to do other things. Yes. I still have great memories of classes completely unrelated to optics or even physics that I took in college, and lots of interests that I'm still discovering under various rocks as I move through life. So I really think it's important to have other things that you're interested in that get your attention. There's enough time at a job. I like what I do. I love what I do, but it's still a job, and sometimes you don't want to think about it too much.
Right. Having other things to balance out with.
But I need distractions when the U of A loses in the basketball tournament. So I need other hobbies that can cheer me up.
So here's my last question then. On the basketball vein, you say that you watch a ton of college basketball.
Yep.
And certainly U of A. I watch more so NBA.
Okay. Well, I know what you're doing later tonight then.
Well, that's exactly correct. Okay. The LA Lakers are thinking about hiring the coach of University of Connecticut, I want to say.
Oh, Hurley?
Yeah.
Okay.
What do you think? Is it good?
Well, okay, I'm a Blazers fan. So I think it's great. Let the Lakers hire him. I think basketball.
You think for Lakers fans it's not going to be great?
Right.
Okay.
Right. Yeah. I mean, college basketball and NBA are just totally different.
Yeah,
You get. Although it's changing with the whole paying the players and just all these transfers that are happening. But yeah, you're good grown men who are making a lot of money and rightfully have egos about their skills, and they don't want to get yelled at in front of their teammates, and it's just a completely different beast. And
I think particularly that team, you have likely some of the bigger egos in that nature.
Yeah.
Okay, well, my guest has been Eric Goodwin. Thank you so much. And with that,
thank you.
Thanks for listening to this episode of the Spotlight Report. As always, we invite you to go to our website, community.eleoptics.com, where you can communicate and discuss this episode of the podcast and find all other episodes of the podcast, as well as other useful information. Thanks. Have a great day.